There are various options for dynamics and secondary motion that can be used with KineFX. For the majority of use cases, you'll be using one of three options. There are, however, a lot of other options, but I will not be covering any of those at the moment. The first option will be spring or physics-based secondary motion. The most common use here will be spring systems, and this will usually be used for things like tails. The other main use case will be ragdoll physics, and both of these options will generally be used to animate the rig, and this animation will generally not be done by the animator. The next major form of deformation will be muscle systems. At the time this video has been recorded, the KineFX native muscle system is currently in beta. This system is based around vellum solvers, although there is also some FEM solver integration. The primary use of muscle systems is surface deformation. Muscle systems are usually focused on small deformations. Most of these deformations would generally be subtle. The system which we're going to be working with now uses finite element methods, also referred to as FEM or FEM. This is a surface and volume deformation system, which is primarily a soft body system. However, it will allow you to simulate muscles. It also helps in the simulation of skin sliding and can help produce wrinkles. And it can allow for dynamic animation of volumes. This is one of the more esoteric features of Houdini. It is a reasonably simple system, and it is incredibly powerful. It also has a lot of advantages in using simulations along with rigging. So now we're going to initialize an FEM solver. In this video, we'll be working on a very basic setup for the solver. First, I'll need some geometry to work with. I'll get a geometry node, and we're going to add some test geometry within this node. The test geometry which I'm going to use is the rubber toy. For the initial simulation, I'll be racing this model. To do this, I'll get a transform node. I'll move this mesh up 1 in Y. This mesh is then going to be converted into solid geometry. This will be done with one of two nodes, either the tet conform node or the tet embed node. In earlier versions of Houdini, these will be called the solid conform and solid embed node, and those names align more closely with the FEM solvers. The reason they had solid in the name is they create what is called solid geometry. Instead of having the mesh as an outer shell, these will create geometry which extends through the volume of the mesh. The easiest way to see what is happening is to use a clip node. I will attach one of these to both my tet conform node as well as to my tet embed node. The difference between these nodes is with the tet conform node, we will preserve our original geometry, where with the tet embed node, we'll generate a polygon cage around our geometry. The tet embed node can actually be better for deformation in a lot of cases. I've attached the clip node, and we can now see what this is doing. So I'll raise the cutting plane. I'll change the viewport mode so that it is flat shaded. Instead of being cut out and hollow, the mesh is filled up with geometry here. One of the things which you'll notice about the geometry which we're currently generating is that the size of the triangles are not particularly consistent. We have smaller triangles near the surface of the mesh. The triangles being generated near the flippers are also smaller, where the triangles at the center of the mesh are quite a bit larger. This can work for basic simulations, and it can work for quick simulations, but this is not ideal for final or more detailed simulations. So if we're doing a more detailed simulation with this mesh, I would want to make the triangles more consistent. With this node, which is the solid conform node, we'd only need to adjust a single parameter, and that parameter is the max tet scale. This mesh is connected to a solid conform, so the scale will be based off our original geometry, which means that in this case we'll need to lower the scale, and this will give us a far more consistent mesh. There is the temptation to lower this further. This, however, will give us far too much detail, and this level of detail will not necessarily lead to better simulation results. We are, however, not going to be using the tet conform node. Instead, we're going to be using the tet embed node. The tet embed node will have two parameters for setting the triangulation of the mesh. Since the exterior has not been defined by geometry, we'll be controlling both the minimum and maximum size of the mesh. When these values become closer to each other, the tetrahedrons will be more consistent in scale. In this case, I'm going to raise the minimum tetrahedron scale. I will also lower the max scale to give myself some more even geometry, as I have very large geometry in the center of the mesh. I'll bring these a little bit closer together as I want to have a reasonably consistent mesh throughout. I'll add a null to reference the end of the network. I'll call this null solid geo, as this is my solid geometry. I'll then need a DOP network, and in this case I'm going to create the DOP network within this network. We can pass the simulation in through the inputs here, however that is not how we'll usually refer to our geometry. I'll enter this node, and we can start to work on the network for the solver itself. We will begin by getting our geometry. This will be done with an FEM solid object node. To set the mesh, we'll work under the deformation tab. The mesh that we're going to be using will be referenced in the initial state. This will need to refer to a tetrahedral mesh. I'll be referring to my null with ... solid geo. And we should now see the geometry which we're going to simulate. The simulated geometry is not necessarily the final geometry for the simulation though, as we can use a tetrahedral mesh for simulation, and we can apply the simulation to our original mesh. To do that, we'll use the final option in this tag, and that would be the embedded geometry field. So with this parameter, I'm going to refer to my original geometry. However, this geometry must be in the same position as the tetrahedral mesh, as the tetrahedral mesh must either be exactly the same size as the geometry, or preferably slightly larger. This is one of the advantages of using the tetembed node, is it will give you that slightly larger cage for the deformation. In this case, I will not refer to the geometry specifically. Instead, I want to refer to it after it's been transformed, so I'll refer to the transform node. I'll do this with ... transform1. We will not see the results of this within the DOP network. Instead, we'll return to the main geometry network, and I'll get a DOP import node. To get the information from our node, we'll need to import the DOP network. I will select the DOP network for the DOP network parameter. This should now give us the simulated geometry, and we want to get the final geometry for our simulation. We'll do this in the geometry data path. In this case, we're going to be referring to our embedded geometry. The display should now change to our original geometry, and we should now be able to see the simulation being performed on our original geometry. Next, I'm going to do a little bit of cleanup on the network. Referring to a transform node is not a good idea. This is not a particularly safe way of working. So I'm going to get a null, and I'll connect this after the transform node. I'll call this the simulation mesh. This is not a particularly great name, but it will work for the moment. I can then return to the simulation. My embedded geometry parameter will now reference my simulation mesh null, and we should now be prepared for creating the actual simulation itself, and we'll perform the most straightforward simulation in order to test that this is working. To perform the simulation, I'll get the FEM solver. I'm also going to get a ground plane. Along with this, I'm going to get gravity. So generally, we'll merge all of our geometry together. To do this, we'll get a merge plane, and I'm going to merge my solid geometry and my ground plane. So we'll have our geometry which has been simulated, and this will be our solid geometry, and geometry which has not been simulated, which is our ground plane. This merge node can then be connected to my solver. This is where our simulation will actually be updated, and this will update the simulation every frame. I'm going to connect my gravity after my solver, and the gravity will be connected to the output. I'll then activate the simulation on the output itself. We can then play to test the simulation. In this case, I'm displaying the simulation itself. There was an error here, but that was because the network hadn't been updated properly yet. If we set our display option to be for our DOP input, we should now see the final simulation applied to our original mesh. So this is our basic setup for an FEM network. To cover it again, we'll need to have our original mesh. We'll need to turn that mesh into solid geometry. The simulation will then be performed within our DOP network. This network can be created at our object level or within a SOP network. We'll perform the simulation within this. We'll start by specifying our solid geometry, which will be the tetrahedral mesh. I will then merge any geometry which is relevant to the simulation. I'm then running my solver. This will run the finite elements method solver. There are actually two solvers within this node. However, that's not something which I'll be looking at yet. And this will give us our basic simulation. Once again, for export, this will actually be done with the solid object itself. We can then use the DOP import node to get the final simulation. And here we can specify the embedded geometry as our final output geometry. So that will give us our most basic FEM simulation, and this is the basis for all simulations which we'll do in the future.